Okay, so this last time we looked at the homonuclear diatomics. Is it not up? What happened? It went off. I guess. Huh. What can happen? Those projector's on. Let me try this again. When all else fails, unplug it and plug it back in. There we go. Yay, here we are. Okay, and so we did homonuclear diatomics. Again, atoms on both sides are the same. Now we're going to look at heteronuclear diatomics, and we're going to get into polyatomic MO diagrams. So for heteronuclear diatomics, or ABs, it's diatomic, right? There's only two atoms, so it's AB molecules. They're all C infinity V. So all homonuclear diatomics are D infinity H. All heteronuclear diatomics are C infinity V. We can classify our different atomic wave functions or orbitals and our molecular orbitals with these different things. So the s orbitals and sigma bonds are z squared. So it's kind of nice, since we know exactly what kind of molecules we're dealing with. We know these symmetries are automatic, you know. The pz, or px and py, are x and y, okay, but so are the pi bonds that they make. So if they're in phase, their symmetry stays the same. If it's px and the px, interacting with each other in phase, then the pi bond is also an x pi bond. And if they're py and py in phase, then the pi bond is a y. So they're both E1. Okay, but if they're out of phase, then that's a pi star. And the symmetry changes to xz or yz, because one is in the x direction in phase, the other is going the other direction in the x direction. And so they have a change along the z axis. And so that's what gives you the pi star bonds. And then the pz orbital is a z, obviously. And so is the sigma star. So sigma stars are out of phase along the z axis. And so the positive z looks different than negative z. And so that's how the z axis is the same way. So it has z symmetry. And so that'll be A1. So it's really easy for a diatomic to assign the symmetries. And we'll get some more practice on that today. Okay. So let's look at just a simple molecule, HF. First of all, let's focus on the atoms. Notice where the H1s is. So your highest orbital, those highest orbitals are going to be roughly the same energy. So I would not have counted off if you had written the 1s orbital right here, right? Because here's the two P's in fluorine, and here's the hydrogen 1s. So they should be close to energy. So if you're writing this phase or MO diagram yourself from scratch, blank sheet of paper for the exam or something, you can put that 1s right up there with the two P's, because that's that frontier orbital. And that's a term you may have heard in organic, but frontier MO theory, maybe not. But those frontier orbitals are roughly the same energy. They're the furthest away from the nucleus. All the interior orbitals have been pulled closer and closer to the nucleus and have shielded those protons, those positive charges. And so in terms of energy, those outer orbitals are roughly the same energy. Okay. Now the symmetry of an s orbital is A1. We just saw that on the previous character table. And the symmetry of the 2s is an A1. And then that pz orbital is also an A1. So this is an important principle. You know, in homonuclear diatomics, we have the same kinds of orbitals on both sides. We have a 2s mixing with a 2s and a 2pz mixing with a 2pz. So we have 4 identical orbitals mixing, and they make 4 MOs. Well, now we have different atoms on either side. So we have different orbitals. So we have a 1s mixing with a 2p and mixing with a 2s. So we're bringing in 3 atomic orbitals, so we're going to get 3 molecular orbitals. So that's a principle. You want to write that down. However many atomic orbitals you have, that's how many MOs you're going to have. So the number of orbitals is conserved. And you can kind of see the shading where we're going with this. Okay. So let's mix these 3 orbitals together and make 3 MOs. Okay. Oh, and we also have the PXPY. So down at the bottom, we have a slight drop in energy for that 2s. In fact, it's really not interacting with the 1s very much. So here's another thing that you can write down. This only moves a little bit. I'll say little interaction. It has little interaction with the hydrogen 1s. Just spatially, thinking spatially, why do you think that is? Looking at the diagram. Yeah. Yeah, they're so different in energy, they don't interact very much. Remember, these are oscillations. And so you can think of these as notes, right? And the closer the notes get together, get close to each other, the more they'll mix. Farther apart, they don't mix very much, okay? And so if you've ever tried to tune a guitar where you play, the 5th fret on the bottom string and you pluck the first 2 strings, if they're close in energy, or close in frequency but not exact, you hear a beat pattern. Wah, 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 as the notes are, the closer they are but slightly off, the more they really interact, okay? If they're identical, you can't really hear it, but they're really strengthening each other. They'll actually be louder, okay? And so they're really interacting if they're identical. If they're close, they interact a fair bit, and you actually get a third tone, the difference, sum and difference. Why sum and difference? Well, it goes to that trig substitution of the cosines times cosine 1 times cosine 2. You get the cosine of 1 plus 2 and the cosine of 1 minus 2, and that 1 minus 2 and is the beat pattern that you hear, the really slow beat pattern. Anyway, some fun stuff there with trig substitutions. Anyway, but if they're far apart in energy, they don't interact very much, okay? And so the PZ and the hydrogen 1s are really going to interact a lot. And so that PZ here drops a fair bit. And then the PZ out of phase goes up pretty high in energy. But that's how we have those 3 interactions. Let's look at the pictures now. Notice there's just a tiny amount of the hydrogen 1s being used here. It's mostly the 2s. And so we're calling this a non-bonded 2s instead of a sigma, okay? So we're saying that 2s really hasn't interacted with the hydrogen, so it's not really a bonding interaction. Whereas this one, this is the PZ interacting with the 1s. You see the PZ orbital here and the 1s orbital on the hydrogen. And there's these essentially have merged. Think of them as water and oil, and these are both water, so they'll suck together and make a single drop. Okay. And you have 1 node. Okay. And then up here at the top, you have the PZ out of phase with the hydrogen, and then you have a second node. So you have a node here, and you have a node there. So it's higher in energy. And this one has a node here from the PZ. So ranked in energy, 0 nodes at the bottom, 1 node in the middle, 2 nodes at the top. It all makes sense, right, in terms of energy. Just be thinking, could I do this? A blank sheet of paper, right? Thinking about, okay, I've got a 2s on the fluorine and I've got a 2pz. How am I going to interact with the hydrogen 1s? It's going to be in phase or out of phase, and everything's going to be happy. Okay. All right, now we have the px and py. They really don't have anything to interact with on the hydrogen, so they just come straight across by themselves. See, there's no hydrogen interaction on this one. So those are really non-bonding orbitals. They can contain electrons, but they haven't spread out over the whole molecule because the hydrogen has no interest in a p orbital. Okay. If you really like this and you want to understand more about this p orbital on hydrogen and what we do when we add p orbitals to Gaussian, we can talk about that later. But I'm really tempted to go down that road, but I'm not, because it's just going to confuse you. But if you add in 2 p orbitals, it will allow these non-bonded orbitals to drop a little bit, because they can move slightly onto the hydrogen, but not much, just a little bit. But it's enough to drop the energy of the molecule, which is what we want in Gaussian. We want the lowest energy molecule that we can have. Okay. Now, the bond order. This is kind of a tough calculation for anything other than a homonuclear diatomic, because I called this one a non-bonding orbital. Okay, so this is the 2 bonding electrons. So this is 2 here, and there are no anti-bonding electrons, so that's 0 there. So 2 minus 0 over 2 is equal to 1. And we know hydrogen fluoride has a single bond, right? HF, single bond. So check. But if we had called this a sigma, then it would be a double bond, right? And so it'd be nice if it matched the bond order. It doesn't always. And in fact, once you get to polyatomics, the bond order calculation goes out the window. So don't get too comfortable with it. Okay. So it's kind of dissatisfying for me that we can't calculate the bond order for polyatomics. Okay, but for diatomics we can. Now, what do we know about this? Well, this is confirmed by the UV photoelectron spectroscopy. We can hit fluorine and we can find out what energy those p orbitals are. We can hit the 1s orbital on hydrogen. So these are from just the atomic signals. We can get 18.6 eV and 13.6 eV from the 2p orbitals or for the 1s orbitals. And then we can hit the molecule and we get a binding energy of 18.8. And then we can get those non-bonded orbitals at 18.6. And then we can actually, through a process called shake-up, sometimes you see a peak in the X-ray or UVPS that has a lot lower kinetic energy, or a lot higher kinetic energy than you expect, and it's because 2 electrons have absorbed the X-ray, and one has ended up in the excited state, and one has taken off some of that excess kinetic energy. Anyway, it's a way to determine what those non-filled orbitals are, and so using that shake-up process, we got the 13.4 eV of that sigma star. And so this is what we would predict with just thinking about the orbitals, and then we go to experiment and we see those same kind of patterns. And so again, MO theory is supported by the structure, the XPS and UVPS. Okay. Let's look at some other kinds of polyatomic. But before I do that, you think you could draw these pictures? I mean, even if you drew the 1s a little too big, that'd be fine. Like if you had F and H, if you drew this as your ground state orbital, like if you were drawing this on a test and you said the 2s plus the 1s, like that would be what you would write. And then this one here, if you drew this, where you had this electron cloud on that, and this over here where the node was kind of on the fluorine, where that's the wave function is equal to the 2pz plus the 1s orbital on hydrogen, then I would accept that, okay? And then up here, if you drew essentially this picture here where you've got that pz orbital on the fluorine and you shade one of them, and then you draw the 1s on the hydrogen. We have the 2 nodes, and then that would be the 2pz minus the 1s. So do you see this sort of the shorthand that I'm using? Here's the 2 s's, they have the same sign, and so they're together. Here the 2pz has the same sign as the 1s, and so I read that as being in phase, and so that's sort of a bonding arrangement. And here they have a different sign. Okay, so that's the important piece that I'm showing here. When they have that different sign, it means they're out of phase with each other. That's just a shorthand for kind of showing you, just on a text line, what what we're mixing. Is everybody comfortable with that? Yes.
Can you explain again why the 1s and 2s orbitals are like so far away from each other to where like they're like non-dominant?
This picture here, or this right here? Okay, so this is what I mean by far away. This energy difference here. Yeah, yeah. So that's why I'm saying little interaction with H1s because of that. Yeah, so they're so far away in energy, which I tried to use that analogy. Energy is vibration. So different frequencies of vibration, and that was the guitar string that I was talking about. Yeah. Cool. Okay, so let's look at a little more complicated MO diagram. This one is done by Gaussian. I calculated the atomic energies. This is for carbon monoxide. Calculate the molecular energy. So I did the atomic sides, both sides, carbon and oxygen. I calculated the molecule, and then I copied those energies from the output file and plotted them. So here's the full MO diagram with the core electrons. And it's nice to show the core electrons because you can see how they don't really move. They don't interact. And so on the left side, we have the carbon atom. On the right side, we have the oxygen atom. Does it make sense that this 1s orbital is so much lower in energy for the oxygen than the carbon? Look at the periodic table. Oxygen has 8 protons and carbon only has 6. And so that 1s gets sucked in much, much tighter, but depending on every proton. In fact, you could look at the energy of the 1s orbital electrons, the binding energy of the 1s electrons, and you would know exactly what element you're talking about. In fact, that's how we discovered most of the periodic table. So a guy named Moseley figured this out, and he made a chart of the 1s energies of all the elements that were discovered before, and he had a linear relationship, and wherever there was gaps, those were elements that hadn't been discovered yet. And then in that order is the order of number of protons in the nucleus. I mean, it was just a beautiful chart, and you could go in and they could say, all right, now we need to take this ore and grind it up and analyze the powder, and if we find a 1s energy that we haven't seen before, we've got a new element in that ore. Let's try to figure out what it is. That was so easy. You didn't even have to separate it from everything else because you would see all the elements you know, and then you see one that you don't know, and you're like, there's a new element here. Let's dig through the dirt and figure out what it is. So I think that was pretty cool. So that 1s orbital will hop up and down depending on the number of protons. And it's so far away in energy from all these others, it doesn't interact. So you will see errors in just about every Gen Chem textbook that will show these 1s orbitals going like this, okay, and interacting, and it's not true, okay, wrong. Spank those folks, that's wrong. They're so far apart in energy that they don't interact, okay. So let's zoom in on the upper part of this diagram. So here's the upper part of the diagram, and I've color-coded it so the A1 orbitals are blue and the E1 orbitals are green. So the 2s and the 2pz are blue and the x and y are green. And I've done that. Now, Gaussian's actually calculating those atomic orbital energies, and you can see that the z, if it's unoccupied, it's higher than the x and y, and the singly occupied orbitals are lower in energy. So when you put 2 electrons in the 2pz, it's higher in energy. Don't worry about that in your drawings. Okay, you can just draw the p orbitals as triply degenerate. That's what I'm expecting. Okay, and so anyway, you could draw this z right here, and that would be fine. I wouldn't be bothered by that at all. Okay, but Gaussian's calculating what Gaussian calculates, so that's great. Notice that the p's on the oxygen and the carbon are close to each other. The oxygen's a little bit lower. Why? Once again, more protons. Okay, so if you're trying to figure out which one to make lower or higher, it's not a lot lower, but it's close. And so then we're ready to interact everything. Now, how many orbitals do I have that are blue? I have 4, and so they're going to make 4 molecular orbitals. And so this 2s and 2pz would interact with the 2s and 2pz on the carbon and form these 4 molecular orbitals in the middle. And so those will be your sigma, sigma star, sigma, and sigma star. So just like the homonuclear diatomic MO diagram, this one looks very similar. Now remember back, if you can, to your notes, does this MO diagram in the middle show sp mixing? It kind of switched places at between nitrogen and oxygen, right? So lithium through nitrogen showed sp mixing, but then once we got to oxygen, that sigma star dropped down below the pi bonds, and that's the way we see it from oxygen on up. And so it's the location of this guy right here. When this is above those pi bonds, and so the px and py make the pi bonds. When that one's above those pi bonds, we're calling it sp mixing, and when that sigma level is below the pi bonds, then we don't have sp mixing. And so we're seeing some sp mixing here. And you can go back to the introduction to MO theory notes to see that discussion of sp mixing. Okay, so the p orbitals make the pi and the pi star bonds, or molecular orbitals. And so let's discuss this Lewis-Dot formula. So we've got the molecular orbital diagram, and then we can also draw the Lewis-Dot formula for carbon monoxide. There's a couple of ways you can draw it. On the left side, we have a double bond, but if we want to fulfill the octet rule, carbon on the left side molecule only has 6 electrons that it can claim. And so we want to share 2 more from the oxygen and make a triple bond. And so on the right, that molecule fulfills the octet rule. So for Lewis-Dot structures, this is one of those molecules where the formal charge and the octet rule oppose each other. So what do I mean by formal charge? Remember from your freshman chemistry, if I divide the covalent bonds in half, then the atoms can claim 1 electron from each of the bonds. And so carbon comes in with 4 valence electrons, and it can claim 4. So it has a formal charge of 0. Whereas over here, it comes in with 4 valence electrons. Let's see, I'm going to run out of space here. So 4 valence electrons, but it can claim 5. So it has a -1 formal charge. And then the oxygen brings in 6, but can only claim 5, and so it has a +1 formal charge. So formal charge is on the right. That octet rule is satisfied, but it has a non-zero or large set of formal charges. If we minimize those formal charges, then we don't have the octet rule. So which is it, right? We would try to figure out what's going on with this molecule. We look at the MO diagram. We can calculate the bond order, right? So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's 8 bonding electrons -2. So we're back down to 6. Divided by 2, that's a 3. So bond order of 3. From our MO diagram. And so it tends to favor the octet rule in this case. Now, which direction does the dipole point? Okay, if we're looking at the octet rule, we see a big old positive charge on the oxygen and a negative charge on the carbon. And so that dipole would be pointing towards the carbon. Now, this is important because if we have a molecule of carbon monoxide and it nestles up to a cation, which end is going to touch the cation, right? Is it going to be the carbon or the oxygen that touches the cation? Okay. And then in this case, we look at the electronegativity in this neutral molecule, and we see 6 electrons on the oxygen. It looks like the dipole points towards the oxygen. Okay. And if we look at the atoms here, carbon had these electrons on it as an atom, and when it bonds, this may be tough for you to understand, but think about this. Okay, listen carefully to what I say here. Carbon has these electrons on it, okay, and its orbitals are right here in energy, and it bonds with oxygen. And look, the oxygen orbitals are very close to all of these in the molecular orbital diagram. And so these kind of slide downhill. You see that? They're sliding downhill in energy to energies that oxygen already possessed. So that's very similar to electrons transferring towards the oxygen energetically. The oxygen orbitals match the molecular orbitals in energy quite a bit. And so this is a transfer downhill, energy downhill towards the oxygen. So those electrons have kind of shifted towards the oxygen. And so we would expect this molecule to have more electron density on the oxygen than on the carbon. Because if we're trying to push it on the carbon, we're pushing it into those atomic orbitals on the carbon, and it goes up in energy. And so we look at Gaussian, and sure enough, it calculates a negative charge on the oxygen and a positive charge on the carbon. A small, it's 0.17 charge units, but still. And so our result is a triple bond from the bond order, but with a dipole that points towards the oxygen. Okay. Yeah. So it doesn't really match either one of these. Okay. As far as the dipole, it matches the octet rule in terms of the triple bond. Okay. So let's look at some of the pictures here. We have this 2s orbital. It's again, it's sort of shifted over towards the oxygen, like we were saying. Here the 2s antibonding, so the 2s on the oxygen, 2s on the carbon. Then we have the px and py, those are the pi bonds. And then this sigma bond here, look, just like we had a lot of electron density here on this oxygen here, we have this bulge on the carbon there. You kind of have these, things set up. If you use a lot of electron density in one orbital on this atom, then you're going to use a lot on the other one in a different molecular orbital. And then here's the pi antibonding, the pi stars. These orbitals here, and then the sigma star. You see the 3 nodes. So you can count up the nodes. Here's 1, 2, 3. This one has 2. They're crossways to each other. 2 planar nodes. This one has 2. This one has 1. This is a planar node here. Same with this one. This one has 1 node, and this bottom one has 0. So just like you expect, as you go up in energy, you have more nodes. Hopefully this is getting boring for you, because you're like, yeah, I can count nodes, right? Okay, maybe not. All right, and so then we have just this sort of foreshadowing into inorganic. Okay, so when you go to advanced inorganic, you're going to make coordination compounds, and one of the ways to make a metal a gas, okay, is of course to boil it, right? But that's a lot, it's energy intensive. Another way is to put organic molecules around that metal so that the metal can't interact with the other metals and have this delocalized bonding, and you just have van der Waals forces then between these molecules, and you can get the metal into a gas phase. Why would we want to do that? Well, we might want to separate these metals and purify them. And so if you could get them into the gas phase, then you could use thermal diffusion, or you could maybe charge them and use mass spec or other ways to do that. But thermal diffusion is one way. And so if we could put carbon monoxide on metals, you could put 6 carbon monoxide molecules on a metal and make it a gas, okay? Or dissolve it in organic solvents, and you could process it that way. And a lot of our catalysis uses this. So advanced inorganic is going to get into organometallics, the mixing of organic molecules and metals, okay? If that scares you, it should. No, I'm just teasing. So this is, again, the orbitals that are useful in sigma donation with pi back donation. So we have an occupied orbital with the sigma bond that has this bulge on the carbon atom. You see that bulge? That big bulge on the carbon atom can interact with the metal d orbitals. And then the d orbitals can interact with this antibonding pi star orbital on the carbonyl. So it's like we can make it's not quite a double bond, but a double association. So a sigma can interact with the metal, and the metal can interact with the pi star on the carbon monoxide. And so this is a very important topic or concept in advanced inorganic. Here's a page from the advanced inorganic textbook. And so that's what's being represented here. This is representing that bulge on the carbon interacting with an orbital on the metal and forming this strong interaction here. And then that's strengthened by a d orbital, like the d xz orbital, interacting with the pi star to form this association here. So that's a really important piece, and that's why this carbonyls really stick to metals. They snap on. You get 6 of them, and now that metal's volatility goes up, its solubility goes up in organic solvents. Lastly, we can go even bigger. I think this is the biggest one I ever show you guys. This is ethylene, or ethene, and this is the MO diagram for ethene. It looks really confusing, but break it into parts, okay? You won't be asked to make this, okay? But if I were to give you any one of these pictures in the middle, you should be able to at least understand what orbitals go into the picture, okay? So let's practice that. First of all, though, the local bond theory produces sp2 hybrids for the carbons, and it would predict 3 types of bonds. So if we did an XPS and we got 3 peaks, that would support local bond theory. Okay, the 3 types of bonds are the CH bonds. So I'm going to put 1 on those. So all of those would be the same kind of bond. And then the sigma bond between the carbons would be a second type of bond. And then the pi bond would be a third type of bond. So those are the 3 types of bonds in the ethene molecule. So if we got 3 peaks in the XPS, that would confirm local bond theory. Y'all watched that video lecture last Wednesday, and so you know what's going on. So here, the projection operator is used, and we'll do the projection operator on Wednesday. Is used to create the symmetry-adapted linear combinations of atomic orbitals. That's a big, long acronym, SALC-AOs. Symmetry-adapted linear combinations of atomic orbitals. And so these are all 4 hydrogens, and these are the 4 combinations you can get by combining 4 hydrogens, all in phase, these 2 in phase with those 2, or with each other and out of phase with the opposite, or top and bottom, or all 4 out of phase diagonally. So, and then you can do the 2 carbon atoms, and that looks like a CC-MO diagram, a diatomic. Okay, you see the sigma, sigma star, pi, sigma, pi star, sigma star, all of those levels. And that's the carbons and carbons mixed together. And then you mix the hydrogens, all 4 of those adapted combinations with the carbon-carbon MOs, and you make ethene. So that's what we have in the middle. So those combinations of the SALC-AOs produce the MOs for ethene. So let's zoom in on the bottom part of this chart. So here we have, again, no nodes for the lowest. That's the 2p orbitals. I'm sorry, the 2s orbitals on the carbons interacting with the 1s on the hydrogens, all in phase, the clouds just oscillating in all directions. Look at this one here, though. This is the 2s on the carbon in phase with the 1s on these sides, and this is the 2s out of phase with the other one and in phase with these hydrogens. So you just have one node down the middle. But then we start getting into the p interactions. So this would be the p orbitals on the p orbitals on the carbons interacting with the hydrogens above and below in phase. And here's it kind of looks like a pi and a pi star, but again, pi and sigma, it's not so clear in a polyatomic, right? It's side-on interaction for the carbons, but it's end-on interaction with the hydrogens. So is it a pi or a sigma? Right? And that's the thing, it's not defined for polyatomics. What I'm trying to say here is this is the p orbital on this carbon. So you should be able to draw what I'm drawing here on the right. Interacting with the hydrogen here, and a hydrogen here, and a hydrogen here that's shaded, and a hydrogen here that's shaded. So you can draw that with just simple p orbitals and s orbitals, shaded and unshaded, and that's what you get for that picture. Okay, this is kind of end-on interaction, so that's a sigma interaction. But this is side-on interaction here, so that's a pi interaction. So We don't know what it is. There's no category for that. It's just a molecular orbital. Okay. It's uncomfortable, isn't it? The sigma and pi really only exist purely for diatomics or linear molecules. But when we get into polyatomics and things going off in different directions, we just have to, this is the language we use. We say this is bonding for the carbon-hydrogen bonds in all 4 cases. So we would say that's a bonding orbital for the carbon-hydrogen bonds. In fact, all of these are bonding except for this one up here. Well, yeah, this one's bonding. This is a pi bond. So that is, we do have a pure pi bond right there. But all the others, you know, they're some form of sigma bonding. Okay, this one is really interesting. This one is sigma star for the carbon-carbon and sigma for the CHs, because the node breaks the carbon-carbon bond. So we would not use the word sigma, really. We would just say it's anti-bonding for the carbon-carbon bond and bonding for the CH bonds. And that's how you would analyze that molecular orbital. And that may be important for your research. Like if you're doing undergraduate research for someone and you do Gaussian calculations, you may want to do some of these MO calculations and say this is bonding for the thing that we are interested in, or anti-bonding for the thing we're interested in.
Could you repeat that? You said it's anti-bonding for the carbon.
Yes.
And bonding for the carbon and hydrogen.
Yes. Mm-hmm. And just look at the picture to explain it. You see it? So that picture there, yeah, so you see it's that node is breaking the carbon-carbon bond. And so that's why I say it's anti-bonding for the carbon bond. And it's the lobe, the green or the red, is going over the carbon-hydrogen bond. Okay, we're out of time, so I'm going to just show you, yes, this produces 6 peaks plus the 1s on the carbon. And so once again, the molecular orbital theory is confirmed by the UVPS. All right.
Sorry, my question.
No, that was good. It was perfect. No, that's perfect.